now that we've defined momentum, I can write Newton's second law in a lovely form, a form that I actually prefer, that the net force acting is equal to the rate of change of the momentum, dp dt. Because we understand now, as Newton did, that the momentum is a more useful quantity. In fact, in the last lecture, I was able to get myself to a place where I implied quite strongly, in fact, you might even say I proved, that the momentum is a conserved quantity, that like energy, it's a symmetry of the universe, a kind of sameness. If I can compute the entire initial momentum of a system and then allow any kind of crazy nonsense to happen, at the end of that, I can calculate the momentum again, and my expectation is that momentum be the same, that number that I can calculate, a certain number of Newton seconds, is unchanged in whatever nonsense nature has going on. And of course, we love symmetries because symmetries give us a way to make predictions and discover new laws and so forth. So it's quite excellent, a remarkable achievement. I also want to point out an aside. When I introduced energy as a symmetry, I said that it was a more complicated symmetry than any of the others that I could identify, because in energy there are many forms of energy: kinetic energy, potential energy, and all the different kinds of potential energy, so on. But momentum is a much simpler symmetry. There's only one kind of momentum, defined only one way. And so the law that I have is the law of conservation of momentum is quite simple. The initial momentum, the total initial momentum of the system, is equal to the total final momentum of the system, and that's it. And from that I derive some consequences. Well, I want to be a little bit more clear than I have been so far about this idea of what I mean as the system. Systems are like coordinate systems. They're completely arbitrary. I choose what objects I want to focus my attention on, and in a sense I draw a conceptual bubble around it. And I say, these items, objects, phenomena are part of my system, and anything outside is external to the system. That's a choice like a coordinate system, and it's arbitrary. But like coordinate systems, some choices are better than others in terms of solving problems. Now, in regard to my version of Newton's second law here, an obvious thing that we did, which I'll repeat now just to make it clear, is to multiply both sides by dt such that the differential of momentum, the differential change in momentum, I'm dropping my vectors, by the way. I'll drop the harpoons. It's still a vector quantity. We know this, that momentum and forces are vectors going forward. That the differential of momentum dp is equal to the net force multiplied by the time dt. Well, obviously, it screams for me to integrate both sides of this equation, so I drop in some integral signs. And what I find is that the change in momentum, delta p, is equal to the integral of the net force acting multiplied by dt. But in the last lecture, I proceeded from a rather important argument associated with Newton's third law, action-reaction, that the action of one body upon another would always be equal in magnitude and directed to contrary parts. So in the context of systems, here's what I'm implying. Imagine I have three quite arbitrary objects. I'm going to use, spheres here because that's like the simplest thing one can describe, I guess, spherical objects. And these three spherical objects can interact the one with the other, perhaps in very complicated ways. For example, A, B, and C here, three objects. If they're interacting with each other under the influence of gravity, it's been discovered that this is actually a very difficult problem to solve mathematically, three objects interacting the one with the other. But I'll say that these three objects are my system, and I will imagine a boundary around the system and say that anything outside of the system is external, and anything inside the system is internal. And A, B, and C are inside the system. When A, B, and C interact with each other, it does not matter the nature of the interaction. According to Newton's third law, those interactions must be action-reaction. And so therefore, the net force on the system will be zero with respect to the interaction forces between A, B, and C. It must be. That does not preclude some external agent exerting a force which I'd call, force external on the system from the outside. That force does not have an action-reaction pair. When we draw, for example, two blocks in contact with each other, a common problem of Newton's laws, we draw two blocks in contact with each other and they're moving perhaps horizontally on a surface. We know that one exerts a normal force upon the other and that those forces are an action-reaction pair. But the reason why we still get some dynamics out of that is that the action-reaction pair is not applied to one object but to both. So when I draw a free body diagram, I draw a free body diagram for one object alone and draw only those forces which act on that object, which is only one of the pair. So action-reaction forces don't cancel out everywhere in the universe because they act on different objects. So here, imagine that the external environment exerts a force on the system. That has a reaction pair. It's the system exerting a reaction force on the rest of the universe. But I don't include that in my diagram.
You made it. Email me here.
But I don't include that force in my diagram. Now, that external force then is unbalanced. So when that external force exists, when I go to compute the sum of the forces dt, all of the internal forces in my system cancel. It's guaranteed. I don't even need to think about it. The forces internal of the system cancel. But it might be more appropriate to write this as the integral of the sum of external forces, dt. And when the external force is non-zero, then that integral is non-zero, and it means that the momentum can change. It means that the momentum can change. So there's a condition on when I can apply the law of conservation of momentum. There can be no external forces acting on what I describe my system. There can be no external force. There can be no external forces. The simplest example of that that I can imagine is when I take an object, which I used to have sitting here, it sat there forever. If I have this eraser, for example, and here it is on the surface, and I give it a velocity. If I give it a velocity, it has a momentum, because it has a mass and a velocity. Mass times velocity is momentum, a certain number of Newton seconds. But then I find as it slides across the table, it slides to rest. It had momentum, now it doesn't. The momentum has changed. I thought momentum was conserved. The momentum has changed because I'm considering the eraser itself. And there are forces external to the eraser, which are changing the momentum. And that is the friction force between the eraser and the table. That's what's changing the momentum, the action of an external force. So what I'd like to do today, by way of example, is give you an example system that's quite interesting and of some historical interest, and is, I think, of some interest to students today who are involved in rocketry as a competitive sport. That's a different debate. As a competition, as a competitive competition, that's redundant. And so what I'm going to consider is the motion of a rocket. So what I need here is to draw my system that I'm going to do for discussion of rocket motion. So I'll draw a rocket, and I enjoy drawing a rocket. I feel like I have some skill at it. Well, now I'm under pressure, and I've done that to myself. So here's my rocket ship. It's got fins like this, right? It's rather attractive. Sometimes when I draw it larger, I like to put rivets on it and whatnot, but there it is. Now that's my rocket, and in principle, my rocket has a mass, but I'm going to describe that mass in two rather obvious ways. It has a total mass, which is the sum of two masses, the mass of the structure of the rocket itself and the mass of the fuel that it carries. Because we know as a rocket motors along, it expends fuel, and I have to include that in my diagram. And so to do that, I'm going to draw some flames here coming out the back of the rocket just for my entertainment, right? Because what happens is a rocket motor produces a controlled combustion process that expels hot gases, which are the combustion products of the fuel, out the back of the rocket, typically through some sort of a nozzle, and I'll come back to that at the end of the discussion. And so what I'm going to do is I'm going to define my system as the rocket, and so I put a dotted line around, making an otherwise pretty diagram look horrible. The rocket and the fuel together is the system. My rocket is in deep space, far from the influence of gravity, which means I have contrived a system here that is completely isolated. Therefore, there are no external forces acting. The only forces acting on this system are the forces between the rocket and the fuel that it expels. If you don't imagine that there's a force there, consider that if I stand here on a skateboard, or actually maybe just on ice, a frictionless surface, if I throw a medicine ball to the left, I will travel to the right. I'm not saying that as a physics concern, but just from your everyday experience. So what's going on in the rocket is technically, through an engineered system, throwing gas, in this case drawn to the left, which propels the rocket to the right. And so there are forces, and those forces are an action-reaction pair. And so what I'd like to understand this rocket motion more. You know, interestingly enough, when some of you know the history of rockets, Goddard, the rocketry pioneer of all time, in Goddard's time, which one was that? It's going to be pre-World War II. It's going to be, I guess, not good to have give a lecture and not know the date of the thing, right? 1900s. Jules is going to look it up for us, so we'll get it in just a second. It was believed that rocket propulsion was not possible because the expelled gases from the rocket didn't have anything to push on, that a rocket in space would not work, because it was imagined that when a rocket was sitting on a launch pad near the surface of the Earth, the expelled gases come out of the rocket, and those expelled gases push on the ground, and therefore the rocket can go up by virtue of the existence of the ground to push on. That is explicitly untrue. It's surprising to me that in 19-teens-ish,
He died.
well, he died in 1945, but let's imagine he did his best work when he was a younger fellow, and certainly it was pre-World War II. It's amazing to me at that time that they were foolish enough to think that there was some sort of problem with action-reaction. It was stunning when I first heard that there was some question about whether rockets would work in space, because naturally they do. I want to understand that motion, and along the way, I'm going to derive at least one fundamental equation of rocketry. Or at least I think I'm going to. Let me give it a try. Because the net external force is equal to zero. I have some consequence. Because the sum of all the forces external to the rocket fuel system, call it forces external. Because the sum of the forces external to the rocket system is equal to zero, the change in the momentum of the rocket fuel system must be equal to zero. Imagine the rocket sitting in space, not moving at all, engines not running. It sits at rest relative to we, the observers, standing there looking at it. It sits at rest, its momentum is zero. The moment it expels fuel to the left, it must proceed to the right, so that its positive momentum is canceled by the negative momentum of the expelled gases, such that the total momentum of the system remains zero, which is what is implied by Newton's second law, or as now we see it, the law of conservation of momentum. If the total change of the momentum is equal to zero, then at any instant in time, the differential change of the momentum is in fact equal to zero. That implies that. And if I integrate dp to get delta p, it would be equal to zero, and so it's totally consistent. It's this differential of momentum that I would like to compute. And so I'm going to do it directly. And so what am I going to do? Well, first of all, I'll mention something that you'll agree with is absolutely true. That the momentum of the rocket is a function of time. The momentum of the rocket is a function of time. And so I'll actually write that explicitly. It's weird that I would do that. I mean, it looks weird to me, but it's true that the momentum of the rocket is a function of time. It is the mass multiplied by the speed. That is the mass of the rocket at any time and the speed at any time. It's all a function of time, which is a little bit daunting. It's a little bit daunting that now not only is the velocity of the rocket a function of time, but its mass is a function of time. I'm actually going to pause here for a moment and point out, this is why the momentum form of Newton's second law is so necessary. If I'm trying to do rocket motion and I use F equals ma, F equals ma doesn't appreciate the fact that the mass of a thing can change as a function of time. And any of you who have done some physics before in a previous class can look back to that and realize that the mass never changed. Right? Mass was never a function of time in any problem that you solved. An object had a mass and it kept that mass all the time. But now I have mass as a function of time, so this could be quite complicated. I'll start out by trying to compute what will the momentum of the rocket be at some future time after it has expelled a certain quantity of mass. And so I'll write it this way. The momentum of the rocket at a future time, and by future time I mean t plus dt, right? So if you want to think about it this way, it's perfectly fine, that t is the initial time, and I'm simply taking an infinitesimal step forward in time, dt. And so the future time is t plus dt. That the momentum at some future time is going to be equal to the change in the momentum, but appreciating the fact that the mass changes and the velocity changes. So I'm going to say that the mass changes as m plus dm. I pause there for a moment because I just made a decision. dm is a negative quantity. I have a feeling that that's going to help me out in my derivation. I could be wrong. Right, because the mass of the rocket is decreasing. So dm is a negative quantity. So when I write m plus dm, that means the mass of the rocket is getting smaller. Of course, the mass of the rocket gets smaller because it is expelling fuel, Blake. Well, then I would be implying that dm was positive, and that's what I'm trying to avoid, right? I'm speculating, Blake. It's going to help me later on with the clarity of my equations. It's only of some utility algebraically. It doesn't mean anything physically. It's a choice that I get to make, and I made it. dm is a negative quantity. dm is a negative quantity. And of course, the velocity of the rocket is quite easy to understand, is going to increase v plus dv. That is, there's a differential change in the velocity. In an infinitesimal amount of time, the velocity of the rocket will increase by an infinitesimal amount. But I have to be careful here, because that is not the final momentum of the system at t plus dt. I have to account for the fact that there is momentum of the mass, the differential of mass that's expelled. So I'm going to write that as the differential of mass that's expelled and consider the exhaust velocity. What am I going to call that? I guess I'll call it VEX. So VEX is the exhaust velocity. Let's go back to when this rocket was manufactured, and some engineers had it in a laboratory, and it was on a bench, it was all bolted down, and they run the rocket engine, and the fuel's expended out. They measure the velocity of the exhaust gases. They're sitting there measuring, and we call that the exhaust velocity. You're going to find out at the end of this, I think, that maximizing the exhaust velocity is one of the goals of that engineering process. And I hope to make it very clear as to why that should be. So there's a certain velocity at which the exhaust gases escape the rocket relative to the rocket. But remember that the rocket itself is moving forward with a velocity v, which is, of course, the objective is to give the rocket, I suppose, the highest velocity that you can. You want to go, 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 go. So I have to be careful what I write here, because the velocity of the gas relative to the rocket is not the velocity of the gas relative to me as I watch the rocket go by. So I don't want to write the velocity of the gas here. I want to write the velocity of the rocket minus why am I writing, sometimes I'm writing uppercase e's and sometimes I'm writing lowercase e's. I don't know. I'm writing lowercase apparently. The velocity of the exhaust, like that. Because I want the velocity of the exhaust relative to me because I'm watching this rocket go by. So the exhaust velocity that I see is not the velocity of the exhaust that the engineers spec the engine at. It's the velocity of the exhaust minus the velocity of the rocket. Oh, Shadi, you wrote it in the reverse order. No, I didn't. I reversed the order because that velocity is in the negative direction according to my coordinate system. All right, so it's a negative velocity, and so I had to reverse the order that I would normally do the subtraction. So now I have a satisfactory description of the momentum of the system after the whole system includes the momentum of the rocket and it includes the momentum of the exhaust. An infinitesimal time dt after the initial time. Well, now I would like to compute. Well, no. I realize that I want to take an algebraic step first here. I apologize. I'm making this up as I go along, so I'm changing what I do as I go. I'm having a fantastic good time, by the way. More fun than I usually have. I think I want to FOIL this out first. This first term here, m plus dm times v plus dv. I think I want to FOIL that out. So I'm going to do m times v. That's the first term. The outside term is m dv. The inside term, I'm going to see it's dm and then v over here. I'm going to write it as vdm because I like to keep I want to keep these variables in front of the differentials. I always like to have the differentials at the end because at some point I'm going to integrate and I don't want variables on the other side of differentials. So I'll write that as vdm, right? And then the last is a strange little critter, which is dm times dv. Oh, that's troubling. The product of two differentials. I don't like that at all. Minus. And I'm going to factor this dm through. I don't want any of these parentheses going on. I don't want them to persist. So I'm going to multiply this through. Minus, again, switching the order of it. It's dm times v, but I'll write it as vdm because that just looks better. And then the negative dm multiplied by the negative exhaust velocity here, or at least negative in that term, is going to be plus v exhaust dm. Again, reversing the order of it in order to get that. That's quite a large term, but it's all of the momentum after some gas, a differential mass dm of gas is expelled. So I want to compute the change in the momentum because that's what's of interest to me, and I know that that change of momentum in the absence of external force should be equal to 0. Yeah. Oh, thank you very much. Thank you very much. I appreciate you guys following along like that. That would have been a catastrophe later on. I would have been. Well, luckily for everyone involved, the rocket would never get off the launch pad because I would never have a suitable equation. Very good. So that's the momentum at some later time t. Now I want to calculate the differential change in momentum, which I know for a fact in the absence of external forces is equal to 0. So the differential of momentum is equal to the final momentum. Oh, you know what? That's a lot to write. I have the VDM here minus a VDM over here. And I want to let you know, just honesty in physics, that dm times dv is bothering me. I don't know what the hell I'm going to do about that. So here's what I'm going to do about it. I'm going to throw it away. Charlie always said you can't throw things away just because you don't like them. I can, because the differential change in mass is the differential change in velocity is infinitesimally small. It is infinitesimally small multiplied by infinitesimally small, which is doubly infinitesimally small, and therefore negligible.
It doesn't become isn't the integral adding up all the changes?
Only when there's a quantity multiplying it. Like if I do the integral of v dt, right? That dt becomes something important because it's being multiplied by v, right? But two differentials multiplied by each other is infinitesimally small,
So
right?
you just had
Right. And if I integrated once, I have two differentials. It would still be infinitesimally small after I integrated it because, we're not speaking about it in a very mathematical way, but it's true. So now I can write a much more compact expression. I'm very grateful. That the mass times the velocity plus the mass times the differential change in velocity plus the exhaust velocity times the differential of mass. That is the final momentum, and I have to subtract from that the initial momentum, which is of course just mv, the mass of the whole thing, rocket and fuel together, moving with a velocity v. Look, once again, I have an mv that appears in the final momentum, and that's not surprising because the initial momentum persists. And I have the initial momentum being subtracted away again, and so I find that the differential of momentum that I was looking for, dp, is in fact equal to m dv plus the velocity of the exhaust, dm. And I'm really happy because I have some memory of how these things are supposed to go, and everything's going my way. Sarah, this is, you know what? I'm going to add an addendum here. I'm going to write that dp, this is going to look a little bit ugly, but you're absolutely right to call me out, is pt plus dt minus p at t. So I took the term from above, the p plus t plus delta t, and I subtracted p of t, which is mv. Okay. It's a change quantity. You're totally right to ask that. I appreciate it that you did. Now my algebra is a little bit dense. I'm not going to put a box on this because I think I'm going to come back to that expression a little bit later on. But for now, appreciate that I made the claim that this is equal to 0. Because I'm assuming here with my system that my rocket ship is far from any other influences. There are no external forces acting on the system. And so dp, the differential change in momentum, should be 0. In fact, if I wait for a longer period of time, the change in momentum overall should be equal to 0. And that's excellent. But if that's equal to 0, then that means that the mass, dv, is equal to the negative of the exhaust, dm. I'm going to divide both sides of this expression here by dt. Divide this by dt and divide this by dt. dv dt on the left-hand side of my equation is something that's very familiar to me. It's mass times acceleration because dv dt is acceleration. So on this side, I have mass times acceleration, which is very familiar. That is a force on the left-hand side. Since I have a force on the left-hand side, whatever remains on the right-hand side, that should also be a force. And what is on the right-hand side is negative, the derivative of the mass with respect to time. I'm going to now introduce a new notation, which I'm going to use many times in our physics as this course goes on. But this is the first time that I'm using it, I think. And that is the dot notation. Have I brought up the dot? I don't think I have. The dot notation is anytime in physics you take a time derivative of something, you write it as that quantity with a dot over it. Oh, that's not right. M dot. M dot is the time rate of change of mass. It's the rate at which mass is being consumed by the rocket engine. This quantity, negative m dot VEX, is a positive quantity. Yes, it's got a negative sign out in front. M dot is negative because dm is negative. I made that choice. So this is some kind of force. Because I know on the left-hand side of the equation it's force, it's ma. So this thing, whatever it is some kind of force. It's a force that has a name that you are very familiar with. I'm so very happy. It's a force that has a name that you're very familiar with. This force is called thrust. I have derived the fundamental equation for rocket thrust. Rocketry equation. Yeah, I'm really excited about it. So, rocketry equation the first. Thrust. That's great. Why do I want rocket thrust? Well, because rocket thrust allows me to change the velocity of the rocket. That's the whole point. Because rockets are a lot easier to get into when they're not moving. So we generally, it's a human failing that we start with our rockets not moving. So you can put a foot in the hatch and get in. So I need to change the velocity of the rocket. I would like to, with my new thrust equation, I would like to determine how much change in velocity can I get. How much change in velocity can I get? So I'll proceed. I'm having so much fun, you don't even know. What? Yeah. Thanks, Jules. I'm just pausing because I'm not sure exactly what I want to do. Here I go. I'm going to go back to this expression. I divided both sides of it by dt, but now I'm going to reiterate that mdv is equal to negative vex dm. I'm going to reiterate that. Because I want to calculate if I have this thrust going on, How much change in velocity do I get? Well, there's the change in velocity dv right there appearing on the left-hand side. You say, well, that's the differential change in velocity. I want the whole change in velocity. What do you think's going to happen? I'm going to integrate dv in order to find the whole change. This is what calculus is all about, right? I've mentioned that early in the introduction of the course. I mentioned about finding what the differential was and integrating the differential to get the whole change would be the activity of doing higher end physics, and that's what I'm doing. So to get dv by itself, I'm going to rearrange this equation by dividing both sides by m. And I'm going to write it in sort of a curious way, because the very next step, you can imagine, I'm going to integrate the thing. And so I want to get it in a form that makes my integration clear, and I know you can't see what I'm writing right now because I keep writing the wrong thing over and over again. dv is equal to negative vex, which, by the way, that exhaust velocity, that's a constant, isn't it? Because the engineers designed the engine to have a certain exhaust velocity. Right? The engine's designed to run at a certain, you would call that the throttle. I suppose there's a lever inside the spaceship. You move the lever back and forth and you set the exhaust velocity. But there's a certain exhaust velocity, and then I'm going to write 1 over m dm, which is a curious way to write that. You might write that dm over m. That would be perfectly appropriate. But when I integrate both sides of this thing, what am I going to get? Well, integrating dv is going to get me delta v, the change in velocity that I get from my rocket, is negative vex, because that's a constant right out in front, the integral of 1 over m dm. And because we're still a little shaky in our calculus, I wanted to write that in such a way that you'd immediately see what I'm integrating. The integral of 1 over m dm is easy. Natural log of m, right? But there are limits on the integration because the rocket, with all of its fuel together, starts out with an initial mass m0, and it burns fuel to a final mass m. It burns fuel to a final mass m. And so what I get by performing this integration is I get, I'm okay, negative vex times the natural log of, I'm exhausting a lot of mental horsepower just making sure that I'm right as I do this. The natural log of m, but I have to evaluate the limits, right? So it's from m naught to m. So what I get is negative the velocity of the exhaust, vex, times the quantity, the natural log of the mass at any time t, minus the natural log of the initial mass. Well, I'm going to absorb that negative sign into that quantity on the end there, and that, as a result, reverse it. So my change in velocity delta v is equal to, taking that negative sign in, the exhaust velocity, vex, I can do it, times the quantity, the natural log of the initial mass, minus the natural log of the mass at any time, thusly. Well, you know what I'm going to do with this. I'm going to apply my natural log rule. There's a lot of squinting going on. I absorb the negative sign, and it reverses the order of this term. Okay. Absolutely. Because I've already, in our course, taken advantage of a property of natural logs that says that the difference of natural logs is the ratio of the natural logs. It's very pleasing. So I'm going to do that here. Oh, well. My marker lacked the endurance. To complete the thing. Vex, the natural log of the initial mass divided by the mass at any time t. And that is equal to the change in velocity. I don't want to do that because, well, I would if I wanted to find the mass of the rocket as a function of time. I would have to do that algebra to get that out. But all I wanted was delta V, and now I have it. I stop. And I have something really remarkable about rocket motion, which is not appealing. This equation tells me how much change in velocity I get in proportion to the exhaust velocity that I engineer. Well, let's imagine that my rocket, I build a rocket that is 90% fuel. Well, look at the space shuttle, for example. See the fuel tank on that thing? Massive. Huge quantities of fuel. So imagine I build a rocket that's 90% fuel, then this ratio, and then I expel all of that fuel, all of it. The best this becomes is the natural log of 10, because I got 10%. If I expel all the fuel, then the mass at the end is just the mass of the rocket itself with all the fuel gone, not zero. I build a rocket that's 100% fuel, and you're flying along in the rocket, you're really happy, like, yeah, this is, oh crap, and it just starts to disintegrate. Bad choice. No, if my rocket's 90% fuel, then there's 10% rocket left over when I've expelled all the fuel, which means this ratio, m naught over m, the best it can be is 10. The natural log of 10, the natural log of 10, quite obviously, is 2.3, which means the greatest change in velocity I can get, which means the greatest velocity that my rocket can obtain, is 2.3 times the exhaust velocity. That's the best I can do. Oh, Charlie, I'm going to build a rocket ship that goes 90% the speed of light. No, you're not, because you're going to have to expel rocket fuel at 90% the speed of light. Good luck. You can't do that. So it's that exhaust velocity that determines the maximum speed that your rocket can obtain. This is the simplest application of the law of conservation. Oh, it's gorgeous. The simplest application of the law of conservation of momentum to rocket motion. I'd like to, at this point, say, look, it's not rocket science, except that it is. It is, in fact, rocket science all the way to the end. The law of conservation of momentum, at least in principle, well, Newton's second law in its momentum form applied to rocket motion.